In this video we're going to talk about multimeters, and because multimeters are funny instruments that can actually take a lot of different measurements, we're going to be focusing specifically on multimeter voltage measurements and root mean square or RMS measurements. So multimeters are really versatile instruments, which is sort of suggested by their name. They combine the ability to measure steady-state voltages, currents, and resistances in one, often portable, package, and that's really pretty handy. Now I've shown three kinds of multimeters on this slide, all of which are in our labs. I want you to pay attention to the idea that the multimeter on the right here doesn't actually look like a little handheld device. It looks like a benchtop instrument, and it's really easy for people to miss these when they're looking around because usually they're looking for a multimeter that looks like this. But don't forget that multimeters can come in a lot of different shapes, including ones that sit on benches. Finally, you usually use needle probes like this in order to measure voltages with a multimeter. In E80, we're mostly going to be using this Elenco LCM 1950 multimeter. This slide highlights the areas of the multimeter that are used for voltage measurements. In order to measure voltage, you need to plug one needle probe into the volt-ohm plug, and you plug the other one into the COM plug. The COM plug is short for common. It's kind of like the multimeter's ground, though we'll talk about that a little more later in the slides. So you wind up using the COM plug for almost every measurement. And this first plug is labeled volts and ohms up here, which helps you remember. Once you have your needle probes plugged into those two holes, you turn the knob over into the voltage section, which is labeled up here, and you need to make sure that you set it to the appropriate value of voltage that you expect to measure. So do you think you'll measure something on the order of 400 millivolts or on the order of 40 volts? The other control that can affect voltage measurements is this button up here, which switches between AC and DC voltage measurements. Once you do that, you can touch your needle probes to the voltage that you want to measure, and the voltage between them will show up on the main screen up here. And that's great, and it's pretty easy to understand how it works for a DC value. A DC value is constant, so one number can represent it pretty well. However, representing an AC value might seem kind of tricky, because that means the voltage is changing. How are we going to fit that onto a screen? So this is actually a tricky enough problem that a special convention has been defined for it. Right, I have a picture of a sine wave on this screen, and already just off the top of our heads we can come up with two different numbers we could use to describe it and possibly display on that screen on the previous slide. We could use the peak-to-peak voltage, labeled VPP here, or the zero-to-peak voltage, labeled VZP. Neither of these are actually what's used. Instead, we use a sort of more clever alternative called root mean square, or RMS voltages. And your multimeter reports those because it makes power calculations very easy. Now, we're going to understand root mean square voltages by calculating the power that this specific wave, this sine wave, would dissipate if it were driven into a resistive load. The instantaneous power dissipated in the load is given by the current in the load at time t times the voltage in the load at time t. The instantaneous power actually changes very quickly if your sine wave is changing very quickly, so it's not suitable for the one number that we're using. So in order to get to that one number, we first take the average of the power dissipated in the load by integrating over one period of the instantaneous power and dividing by the period. Now, because we know we're driving into a resistor, we can replace I of t with V of t over R. And because, for this example, we know our voltage wave is a sine, we can replace V of t with VZP times sine of 2 pi over the period times t. So that gives us this integral that we need to evaluate. And the trick to doing that is to factor out all of the constants, so VZP squared over R. And then remember that the integral over one period of sine squared is 1/2, which is totally a thing that's worth memorizing. And that means that the average power that a sine wave dissipates into a resistor, this P average res sine, is equal to VZP squared over 2R. So the RMS voltage is defined as the voltage that would dissipate the same amount of power in a resistor R that this wave does. VRMS squared over R is defined as being equal to the P average into a resistor, which means that our RMS voltage is equal to VZP over the square root of 2 for a sine wave. Now, notice that this RMS voltage will actually depend on the shape of the wave. Like the RMS value of a square wave is quite different, which is a fun brain teaser for you to think about on your own. What you're mostly going to be measuring is sine waves, so VRMS is equal to VZP over radical 2 for a sine wave. Alright, so everything before this slide has been describing the basics of how a multimeter works, just kind of how to operate it. Now we're going to talk about the kind of interesting theory of a multimeter. In particular, we're going to be taking this voltage measuring multimeter and trying to fit it into the big ideas of electrical measurement from our previous video. So the first thing that we have to ask is, what's the equivalent circuit of a multimeter? And it's shown on this slide. Now, we know that our multimeter is taking a voltage measurement, so we have this ideal voltage measurement over here. And when you hook up voltage measurements to a circuit under test, you want to hook them up in parallel. So we can see that the equivalent circuit model of our multimeter, which is everything outside of these little terminal indicators here, is hooked up in parallel with our circuit under test. It turns out that the equivalent circuit just looks like a big 10 mega ohm resistor. So when you take a voltage measurement with your multimeter, you're putting a big 10 mega ohm resistor in parallel with the circuit under test between the two terminals of the multimeter. Now, 10 mega ohms is a pretty big number. We're also going to use this model to talk about loading. 10 mega ohms is a pretty high resistance, so it's really unlikely to steal much current from your circuit under test, right? Current that runs through here would only do so if the circuit under test appeared to be higher impedance than 10 mega ohms, or sort of a comparable impedance to 10 mega ohms. So that means that your multimeter is unlikely to load resistances unless the resistances are very large. Or put another way, your multimeter presents a low loading by having a very high Rin. So the last of our big ideas asks what reference our instrument uses when it takes a voltage measurement. In the case of the multimeter, it just uses its own COM port as a reference, which means that it can be connected between almost any two voltages, sort of anywhere in your circuit, without affecting them. And this is actually a remarkably cool property, which is called taking an isolated measurement, and it's way trickier to implement than you'd guess. There's a hidden shorthand saying that this multimeter is taking an isolated measurement in this equivalent circuit. There are no ground terminals anywhere on it, so that means the measurement is just between the two terminals. And this, by the way, is the equivalent circuit of the multimeter with the circuit under test taken off. Even though you can attach the multimeter anywhere and it won't electrically cause a problem, there are still ways you can mechanically cause a problem with your multimeter because you're putting big pieces of metal onto your circuit. So make sure you don't slip up and accidentally touch two contact points on your circuit with the same needle probe, because you'll cause a short between them. So to summarize, multimeters are tools that contain multiple instruments which can measure steady state voltage or current or other stuff. And multimeters represent AC measurements. Using RMS or root mean square values. The equivalent circuit for your multimeter when you're taking a voltage measurement is just a big 10 mega ohm resistor that sits between the volt ohm port and the COM port, which means that it doesn't load many circuits because 10 mega ohms is much bigger than most resistances you'll measure. And multimeters take floating voltage measurements, so they're safe to plug in almost anywhere.